Another example of an object undergoing simple harmonic motion is a simple pendulum. A simple pendulum consists of a mass suspended by a rope. And as long as we assume that our rope has no mass, and as long as we neglect any type of friction between the air molecules and our mass, well, then we can assume that our object, our simple pendulum, is experiencing simple harmonic motion. Now, actually, that's not exactly true, because we also have to make a third assumption, which we'll talk about in just a moment. First, let's look at our simple pendulum diagram. So we have the ceiling, we have the rope, and we have our mass. Let's suppose we begin at position 1, so we move our mass to position 1 and we let go. Our mass will begin to swing back and forth, and as long as we neglect friction and the mass of our cord, well, then the object will continue swinging back and forth endlessly. So it will move from position 1 to position 2 to position 3, back to position 2, and finally back to position 1. And this is one full cycle of our oscillation. Now, position 2 is usually assumed to be the equilibrium position, because the angular displacement with respect to our y-axis at this position is assumed to be 0. Now, notice that points 1 and 3 represent our maximum displacements. So this is the positive maximum displacement and the negative maximum displacement. Now, let's examine our object, the mass, at position 1. We want to determine all the forces that are acting on our object at position 1. And then we want to use those forces to determine the actual force that creates our oscillating motion, that allows our object to swing back and forth. So let's look at the following diagram, and we're only looking at position 1. So at position 1, we have two forces acting on the object. We have the tension in the cord that points along the cord in this direction. And we also have the force of gravity that's pulling downward on our mass. So this force of gravity has two component forces acting on our mass. We have this component force, m times g times cosine theta, and this component force, which is m times g times sine theta. Notice the theta is simply the angle that the rope makes with our imaginary y-axis shown in orange. So if this angle is theta, this angle is also theta, and that means we get mg cosine theta for this vector and mg sine theta for this vector. Now notice there is no motion along this axis, so that means these two forces are equal, but we do have a net force acting on the mass that points in this direction, and that net force is a result of mg sine theta. So this is the force that creates our oscillating motion. So F is equal to negative mg sine theta. Now, what exactly is theta? Where theta is also known as the angular displacement of our object. And recall that the angular displacement of the object given in radians is equal to x, our displacement along the following arc, divided by L, which is the length of our rope. So if we rearrange this equation, we see that our displacement of the object along this arc is equal to our angle in radians that the rope makes with respect to our vertical axis, also known as our angular displacement, multiplied by L, our length of the rope, given in meters. So, before we continue with this step, let's go back to this formula. So, this formula tells us that the force acting on our object, that's propelling the object to swing back and forth, is directly proportional to the sine of the angular displacement. Now recall, by definition, whenever an object is undergoing simple harmonic motion, the force that object feels is directly proportional to the displacement. And in this case, the force is directly proportional to the sign of our displacement. So that means our swinging pendulum is not really undergoing simple harmonic motion. However, notice that if we allow our angle that the rope makes with respect to the vertical axis to be very small, then that angle is approximately equal to sine of that angle. In other words, when the angle is small, we have the following approximation. So that means force, which is equal to negative mg sine of the angle theta, is approximately equal to negative mg of the angle theta. Because when the angles are small, these two quantities are approximately the same. And now we have the following equation. Force is approximately equal to negative mg of the angle displacement, and we see that our force is now directly proportional to our angle displacement. So that means when the angle is small, is assumed to be small when there is no friction, and when the mass of our cord is assumed to be zero, then our object, our simple swinging pendulum, is undergoing simple harmonic motion. Now, notice from this result, because our angular displacement is equal to x divided by L, we can replace our theta with x divided by L, and we get the following result. So our force is approximately equal to negative mg divided by L multiplied by our displacement. And if we equate this to Hooke's law, then we see our K, our stiffness constant, is negative mg divided by L, where the negative simply means that our force acting on the object is in the opposite direction of our displacement. So this quantity is our K, so K is equal to mg divided by L. Now recall the equation that relates our angular frequency omega, our stiffness constant, and our mass. So the equation states that our angular frequency is equal to the square root of K divided by M. And because K is equal to mg divided by L, if we plug this quantity into K, the m's will cancel, and we'll see that our angular frequency is equal to the square root of g divided by L. And because our angular frequency is equal to 2 pi times the frequency, we see that the frequency is equal to 1 divided by 2 pi multiplied by g divided by L, the square root of g divided by L. So this equation is very important because it tells us that if our angle is relatively small of our simple pendulum, as the pendulum swings back and forth, the actual frequency does not depend on the amplitude, and it does not depend on our mass of the object. So if we have a large mass or a small mass, the frequency will be exactly the same as long as our length of the rope is the same.